Every teaspoon you have ever held has told you the same quiet thing. A spoonful is a small amount, a light amount, something you could lift without a single thought. But there is a place in the universe where one ordinary teaspoon of material would weigh 5 billion tons. Not a heavy spoonful. 5 billion tons, the weight of a mountain balanced on the end of a spoon. It comes from the crushed corpse of a dead star, a city-sized object barely 20 kilometers across that holds more mass than our entire sun. Its gravity is so violent that light bends around it, so that if you stood on its surface, you could see the back of your own head. It spins 716 times every second. It carries a magnetic field strong enough to erase a credit card from the distance of the moon. And the strangest part of all is that it is made of exactly the same matter as you are, simply pushed one step too far. So, what really happens when you take ordinary matter and squeeze it until it cannot be squeezed any further? Get comfortable. Hit subscribe if you're new here, because by the end of this, the word heavy will never feel the same in your hand again. Now, let's slowly ease into this. Part 1. The spoon that outweighs a mountain. There is an object out there, scattered through our galaxy in the hundreds of millions, where a single teaspoon of its material would weigh more than a mountain. Not a heavy spoonful, not an unusually dense spoonful. A spoonful that, if you could somehow lift it to the surface of the earth and set it on a kitchen table, would weigh as much as a mountain range and would punch straight through the table, through the floor, through the planet's crust, falling under its own impossible weight. That single spoonful would tip the scales at billions of tons. I want you to sit with that number for a moment, because everything else we talk about tonight grows out of it. We are not talking about a metaphor. We are not exaggerating for effect. Somewhere above you, right now, there are objects where matter has been crushed so completely that the rules you live by simply stop applying. They are called neutron stars, and they are, by almost every measure, the most extreme stable things in the universe that are not black holes. Picture a city. Picture the span of streets and buildings from one edge of a large metropolitan area to the other, perhaps 20 kilometers across, perhaps a little more. Now imagine taking the entire sun, a ball of fire so large that you could fit more than 1 million Earths inside it, and crushing all of that mass down until it fits inside that city. Not a fraction of the sun. More than the whole of it, somewhere between 1 and 2 times the sun's mass, squeezed into a sphere you could drive across in 20 minutes. That is a neutron star. It is the corpse of a dead star, and it is so dense that the matter inside it no longer resembles anything you have ever touched. The gravity at the surface of such an object is so violent that it does something almost no one expects. It bends light. Not in the gentle way a glass of water bends a straw, but so severely that the path of a beam curves around the star, like water running around a stone. If you could stand on the surface and look straight out toward the horizon, the light leaving the back of your own head could curve all the way around the star and return to your eyes from the front. You would, in a real and measurable sense, be able to see the back of your own head. Hold on to that image, because we are going to come back to it, and when we do, you will understand exactly why it happens. For now, I only want you to feel the strangeness settling in. Almost everything you believe about matter is built on a quiet assumption, the assumption that solid things are solid, that heavy things have a sensible weight, that the floor beneath you is a firm and final fact. A neutron star takes that assumption and very calmly dismantles it. The atoms that make up your chair, your hands, the walls around you are mostly empty space. If you remove that empty space, if you crushed the emptiness out of ordinary matter the way a neutron star does, your entire body would shrink to something smaller than a grain of sand, and it would still weigh exactly what you weigh now. That is not a trick of language. That is what a neutron star is. It is what is left when the universe calls the bluff of ordinary matter. These objects spin too, and not slowly. Some of them turn faster than a kitchen blender, hundreds of complete rotations every second, while carrying more mass than the sun. They carry magnetic fields trillions of times stronger than the field that turns a compass needle on Earth. Fields so strong they would erase the data off a credit card from the distance of the moon, fields so strong they distort the empty vacuum of space itself. And, on rare occasions, two of these objects find each other, spiral together over millions of years, and collide in a flash that briefly forges gold and platinum and scatters it across space. The gold in a wedding ring may well have been made this way, in the collision of two dead stars long before the Earth existed. So tonight we are going to do something simple and slow. We are going to take this one impossible object apart, piece by piece, and look at how each piece is even stranger than the last. We will start at the very beginning with how a neutron star is born, because the birth is a catastrophe on a scale that is hard to hold in the mind. We will watch a giant star die. We will follow its core as it collapses in less than a second. And then we will descend, layer by layer, into the thing it leaves behind, all the way down to a question that physics still cannot answer. There is a reason I called this the terrifying science of neutron stars, and it is not because they are coming for us. Almost every one of them is so far away that it could never touch your life. The fear is quieter and stranger than that. The fear is that these objects are real, that they are measured and confirmed and sitting in our data, and that they prove the universe routinely runs on rules that make no sense to a human standing on solid ground. A spoonful that outweighs a mountain is not science fiction. It is a fact about the sky above you. And by the time we are finished, the ground under your feet may feel just a little less solid than it did when we began. It helps to know that these objects are not rare freaks, not one-of-a-kind curiosities tucked away in some forgotten corner of space. Our galaxy alone is thought to contain somewhere between 100 million and 1 billion neutron stars. They are scattered everywhere through the Milky Way, drifting between the ordinary stars, most of them dark and silent, and far too faint for us to notice. We have detected only a few thousand of them, a tiny sliver of the enormous population that must be out there, which means that on any clear night, when you look up at the soft scatter of stars, you are also looking, without knowing it, past an unseen crowd of these crushed and spinning remnants, hundreds of millions of dead stars hidden in the spaces between the living ones. I want to be careful about the word terrifying, because it can be misunderstood. These objects are not a threat to you. They will not arrive one day and do you harm. Almost every one of them is so impossibly far away that it could never affect a single moment of your life. The fear they inspire is not the fear of danger. It is something quieter and harder to shake. The fear that comes from realizing that the universe you live in is not the calm and sensible place your instincts assume it to be. We walk through life trusting that matter is solid, that weight is sensible, that the rules we feel around us are the rules everywhere. A neutron star is the proof that this trust is local, a comfort that holds only here, on the gentle surface of a small planet, and that just out of sight, the same matter we are made of is being treated in ways that would unmake us in an instant. There is a strange peace to be found in that, once the initial vertigo passes. The universe is far larger and far stranger than the small, solid world of our daily experience, and a neutron star is one of the clearest windows into just how strange it really is. To look closely at one of these objects is to feel the boundaries of the ordinary dissolve, gently, the way the edges of the room dissolve as you fall asleep. So let yourself feel that loosening. There is nothing here that can reach you. There is only something true and astonishing, waiting to be understood. So get comfortable and let your breathing slow. because we are about to leave the world of ordinary weight behind. The first thing we need to understand is not the neutron star itself. It is the death that makes one possible. Part 2. How the universe builds a monster. Every neutron star begins its life as something soft and slow and almost gentle. It begins as a cloud. Out in the spaces between the stars, there are enormous clouds of gas and dust, mostly hydrogen, the simplest and oldest material in existence, drifting in the cold and the dark for millions of years. These clouds are thin, far thinner than the air you are breathing, but they are also unimaginably large, stretching across distances that light itself takes years to cross. And within them, very slowly, gravity goes to work. Gravity is patient. Wherever the cloud is a little denser than average, it pulls a little harder, and that extra pull draws in a little more material, which makes it denser still, which makes it pull harder again. Over a span of time longer than human civilization has existed, a knot in the cloud collapses inward on itself, growing hotter and denser at its center as it falls. The falling material has nowhere to go but inward, and as it piles up, the pressure and the temperature at the core climb higher and higher until something extraordinary happens. The center of that collapsing cloud becomes hot enough and dense enough to ignite nuclear fusion. A star switches on. That moment of ignition is the beginning of a long and stable life. In the core of the newborn star, hydrogen is being fused into helium, and that process releases an enormous outpouring of energy. The energy pushes outward, a relentless pressure of light and heat trying to blow the star apart, and gravity pulls inward, trying to crush it down. For most of a star's life, these two forces hold each other in a near-perfect balance. The outward push of fusion exactly answers the inward pull of gravity, and the star sits in that balance, burning steadily for an immense span of time. For a star like our Sun, that balanced life lasts about 10 billion years. But not all stars are like the Sun, and the ones that make neutron stars are the giants. When a star is born with many times the mass of the Sun, 8 times, 15 times, 20 times or more, its life is utterly different. The greater mass means greater gravity, and greater gravity means the core is squeezed harder and burns hotter. A massive star is like a fire, fed far too much fuel at once. It blazes with a fury that can make it tens of thousands of times brighter than the Sun, and it burns through its hydrogen at a reckless, extravagant pace. A star 20 times the mass of the Sun does not live for 10 billion years. It may live for only a few million. The biggest, brightest stars in the sky are also the ones racing fastest toward their ends. When such a star begins to run low on hydrogen in its core, the long balance starts to falter, and the star enters the strangest chapter of its life. With the hydrogen running out, the core contracts and heats further, until it becomes hot enough to fuse helium, the ash left over from the first round of burning. Helium fuses into carbon and oxygen. When the helium runs low, the core contracts and heats again, and begins to fuse those heavier elements in turn. The star is now burning in layers, like the rings of an onion, with the heaviest elements forming deepest in the core and lighter elements burning in shells above them. Carbon fuses into neon and magnesium. Neon and oxygen fuse into silicon, and silicon fuses into iron. It is worth pausing to notice that this layered burning is also where most of the ordinary world comes from. The carbon in your body, the oxygen you breathe, the silicon in the rocks, and the sand and the glass around you, all of it is forged in the cores of massive stars during exactly this chapter, the slow climb up the ladder of elements in the years before the collapse. A dying giant is a factory building the raw material of planets and people, element by element, and when it finally explodes, it scatters that material across space to become part of new worlds. So even before we reach the neutron star, the death of a massive star is already one of the most generous events in the universe. seeding the cosmos with the ingredients of everything that will come after. The same catastrophe that builds the monster also builds the matter that monsters and planets and living things are made from. While all of this is happening deep inside, the outer layers of the star swell enormously. The star bloats outward into a red supergiant, expanding to hundreds or even thousands of times its original size. If you placed such a star where our sun sits, its surface would swallow the inner planets entirely and reach far out into the solar system. From the outside, it looks like a slow and stately giant, glowing a deep furnace red. But inside, a clock is ticking down with terrifying speed, because the star has finally reached the one element that it cannot use. That element is iron, and to understand why iron is the end, you have to understand what fusion has been doing all along. Every fusion reaction up to this point has released energy. Fusing hydrogen into helium gives off energy. Fusing helium into carbon gives off energy. All the way up the ladder, each step pours out the energy that holds the star up against its own gravity. But iron is different. Iron is the most tightly bound nucleus there is, the bottom of the well, and when you try to fuse iron into something heavier, the reaction does not release energy, it consumes energy. It takes more than it gives. This is the trap the star has been digging for itself for millions of years. The moment the core becomes iron, the fire that has held the star up for its entire life cannot continue. The outward pressure depends on the energy of fusion, and iron cannot provide it. The balance that has lasted for the star's whole existence, the steady standoff between the crushing weight of gravity and the outward push of the fire, is about to be broken. And gravity, which has waited patiently for millions of years, is about to win. The burning of each successive fuel happens faster than the last, and the final stages race by with shocking speed. A massive star might spend millions of years fusing hydrogen, then perhaps a million fusing helium, then centuries fusing carbon. But the burning of neon may last only about a year. The burning of oxygen, only a matter of months. And the final burning of silicon into iron, the last fuel the star will ever have, lasts about a single day. In the last day of a star's life, it is quietly building the iron core that will be its undoing, and it has no way to know that the end is hours away. It is worth pausing on how cruel and elegant this trap really is, because it reveals something profound about why the universe is built the way it is. The energy that holds a star up is not free. Every second of a star's life, it is paying for its own existence by fusing lighter elements into heavier ones and pocketing the energy that pours out. The star is, in effect, running a furnace that funds the pressure holding it open against gravity, and for most of its life, the furnace runs at a healthy profit. Hydrogen into helium is a tremendous bargain, releasing a great deal of energy for very little fuel. As the star climbs the ladder to heavier elements, each step still pays, but it pays less and less, and it burns through fuel faster and faster, like a business whose margins are shrinking while its costs are soaring. By the time the star reaches iron, the furnace has stopped paying altogether. Iron is the point where the books finally balance against the star, where fusion can no longer fund the pressure that holds it up. And the star cannot choose to stop. It cannot decide to coast on what it has. The instant the energy stops flowing, gravity, which has been pressing inward without pause for the star's entire existence, finds nothing pushing back. There is a terrible inevitability to it. The very process that kept the star alive for millions of years has been, all along, marching it toward the one element that would kill it. The brighter and more massive the star, the faster it races down this road, which means the grandest, most luminous stars in the universe are also the ones rushing most eagerly toward their own collapse. When that iron core grows past a critical limit, about 1.5 times the mass of the Sun packed into a ball roughly the size of the Earth, it can no longer support its own weight. There is nothing left to push back. And what happens next is one of the most violent events the universe is capable of producing. A collapse so fast and so complete that it takes less time than the blink of an eye, And out of that collapse, in that single shattering instant, a neutron star is born. Part 3. Collapse in less than a second. The collapse begins in silence. There is no warning at the surface, no flicker that the outer layers of the star can perceive, because the catastrophe happens at the very center, hidden under hundreds of thousands of kilometers of glowing gas. The iron core, having reached the limit it cannot exceed, simply gives way, and once it begins to fall, there is nothing in the universe gentle enough to stop it. To grasp the speed of what follows, you have to let go of every ordinary sense of how long things take. The iron core is about the size of the Earth, and it is about to shrink to the size of a city. On Earth, a journey from one side of the planet to the other is something we measure in hours of flight. The core makes that entire journey of collapse, from planet-sized down to city-sized, in considerably less than 1 second. The inner regions fall inward at speeds reaching a quarter of the speed of light, tens of thousands of kilometers every second, plunging toward a center that is becoming more crowded and more crushing with every passing instant. As the core collapses, the pressure climbs to a level that does something no ordinary material can survive. In normal matter, atoms hold their shape because the electrons around them refuse to be pushed into the same space. This stubbornness of electrons is one of the quiet rules that keeps the world solid. It is the reason your hand does not pass through the table. But, in the collapsing core, gravity becomes so overwhelming that it overrules even this. The electrons are crushed inward, forced to merge with the protons inside the atomic nuclei, and in that merging, a transformation takes place. Each electron and proton combine to become a neutron. This process is called electron capture, and it is the moment the core stops being ordinary matter and starts becoming something new. In that instant, almost the entire core converts into neutrons, packed together with a tightness that has no parallel anywhere in your experience. The atoms are gone. The empty space inside them, the vast majority of what ordinary matter actually is, has been squeezed completely out. What remains is a single, continuous mass of neutrons, pressed shoulder to shoulder, a substance so dense that it behaves more like one gigantic atomic nucleus than like anything we would call a star. The collapse finally halts, not because gravity gives up, but because the neutrons themselves refuse to be compressed any further, pushing back with a pressure born from the deepest rules of quantum mechanics. When the falling material slams into that suddenly rigid neutron core, it rebounds. Imagine a tremendous weight dropped onto an anvil that does not budge. The impact throws everything backward. A shock wave is born at the center and begins to race outward through the still falling layers of the star. But the shock wave alone is not quite enough to finish the job. And here the story takes a turn that took physicists decades to understand. The true engine of the explosion is something almost ghostly. When the protons and electrons merged into neutrons, they released an unimaginable flood of tiny particles called neutrinos, and they carried away the overwhelming majority of the energy of the collapse, around 99% of it. Neutrinos are famous for almost never interacting with anything. Trillions of them are passing through your body as you listen to these words, and not one of them touches you. They can cross light years of solid lead without slowing down, and yet, in the heart of a collapsing star, the matter is so incomprehensibly dense that even these ghostly particles cannot escape cleanly. A small fraction of them deposit their energy into the surrounding layers, and that is enough. The stalled shock wave is reignited, lifted, and driven outward with renewed force. The outer layers of the star, millions upon millions of kilometers of material, are blasted off into space. This is a supernova. And the scale of it is something the human mind can state, but never truly feel. For a brief span of days to weeks, a single exploding star can shine as brightly as an entire galaxy of hundreds of billions of stars combined. In those first few seconds, that one dying star releases more energy than our Sun will produce across its entire 10 billion year lifetime. People on Earth have seen these explosions with the naked eye across the span of recorded history, bright enough to be visible in daylight, appearing as new stars in the sky where none had been before. What they were seeing, without knowing it, was the death cry of a giant and the birth announcement of something far stranger. Because when the light fades and the blasted-off gas drifts away into space to form a glowing wreck, something is left behind at the center. The supernova is the explosion. The neutron star is what survives it. There, in the place where the iron core used to be, sits a sphere of pure neutron matter, about 20 kilometers across, carrying more than the mass of the Sun, still glowing with the leftover heat of its violent birth, already spinning, already wrapped in a magnetic field of monstrous strength. What is left behind, though, depends entirely on one number, and that number is mass. If the collapsing core is below a certain limit, the pressure of the neutrons is enough to halt the fall, and a neutron star is the result. But if the dying star is heavier still, if the core that collapses is too massive, then not even the fierce resistance of the neutrons can hold. The collapse does not stop at the neutron stage. It continues, past every limit, crushing the matter down toward a single point, and a black hole is born instead. A neutron star, then, is a thing balanced on a knife's edge. It is matter stopped at the very last instant before it would vanish entirely. It is one step short of a black hole, frozen at the edge of the abyss, held back only by the refusal of neutrons to be pushed even one step too far. It is worth dwelling on the role of the neutrinos for a moment, because it is one of the most beautiful and counterintuitive parts of the whole event. Neutrinos are the most antisocial particles we know of. They almost never interact with ordinary matter at all. A single neutrino could pass through a wall of solid lead many light years thick and most likely emerge on the other side untouched. Right now, as you rest, trillions upon trillions of neutrinos from the Sun are streaming through your body every second, and not one of them so much as nudges an atom of you. They are, for nearly every purpose, ghosts. And yet, in the heart of a collapsing star, the matter is packed so unimaginably tightly that even these ghosts cannot slip through. For a few seconds, in that one place in the universe, the densest object short of a black hole becomes opaque to the particles that pass through everything. The neutrinos pile up, lend a fraction of their energy to the stalled shock wave, and that fraction is enough to blow the star apart. The most explosive event in the cosmos is powered by the particles that almost never touch anything. Consider also what it means that the supernova is mostly invisible. When you picture an exploding star, you imagine a flash of blinding light, and there is indeed light, enough to outshine a galaxy. But the light is only about 1% of the story. The overwhelming majority of the energy, that 99%, leaves in the form of neutrinos, an invisible flood that washes outward through the universe, carrying nearly all the fury of the collapse. We confirm this in a remarkable way. When a relatively nearby star exploded and its light reached Earth, our detectors deep underground caught a brief patter of neutrinos arriving a few hours ahead of the visible flash, the ghosts running out in front of the light, exactly as the theory predicted. We had, in effect, felt the star die before we saw it die, and the timing matched what the equations demanded. The collapse you are picturing is not a story we pieced together from guesses. It is something we have measured, particle by particle, from across the gulf of space. That balance, that razor-thin margin between the densest visible object in the universe and the disappearance of matter altogether, is what makes a neutron star so fascinating and so unsettling. It is not a stable, comfortable thing. It is a catastrophe caught and held in mid-fall. And now that we understand how it forms, we can finally turn to the property that makes everyone who hears about it stop and ask whether it can possibly be true. We need to talk about how much a neutron star actually weighs. Part 4. The weight of a single spoonful. Let us return now to that spoonful, because it is time to understand it properly. The density of a neutron star is the single hardest thing about it to believe, and it is also completely real, confirmed by decades of observation. So I want to build it up slowly, with comparisons you can actually hold, until the number stops sounding like a mistake and starts sounding like the truth that it is. Start with something small and ordinary. Take a single sugar cube, the kind you might drop into a cup of coffee, about 1 centimeter on each side. On Earth, a sugar cube weighs almost nothing. You could balance 100 of them in one hand. Now imagine that same little cube, the same tiny volume, but filled with the material of a neutron star instead of sugar. That cube would weigh somewhere in the range of hundreds of millions of tons. A single cube the size of your fingertip would outweigh every car, every truck, every ship and skyscraper in a large city, all of it combined, pressed into a space you could close your fist around. Now, scale up just slightly to a teaspoon. A teaspoon of neutron star material would weigh in the billions of tons. By many estimates, it lands near 5 billion tons, a single spoonful weighing as much as a mountain. If you could somehow hold that spoon level for even an instant, it would not stay in your hand. It would fall through your hand, through the floor, and keep falling, because nothing in the ordinary world is strong enough to hold up 5 billion tons concentrated into the size of a spoonful. The matter would plunge straight into the Earth and not stop until the planet's own resistance slowed it deep below the surface. This is not poetry. This is what happens when you remove the empty space from matter. Everything you have ever picked up, everything you have ever called heavy, is mostly nothing. An atom is almost entirely vacant. If the nucleus of an atom were the size of a marble, the nearest electron would be something like a kilometer away, with nothing in between. All the solidity you feel in the world, the weight of a stone, the firmness of a wall, is the structure of that emptiness holding its shape. A neutron star is what you get when that emptiness is gone, when matter is packed as tightly as the nucleus of an atom, with no gaps left at all. I want you to feel how strange that makes your own body. The chair you are sitting in feels solid. Your own hand feels solid. But if you could squeeze a human body the way a neutron star squeezes matter, removing all the empty space inside every atom, the entire body would shrink to something far smaller than a single grain of sand, and that speck would still weigh as much as the whole person does now. Solidity is a kind of illusion. It is real enough to hold a coffee cup and to keep you from falling through the floor, but it is a bluff that the universe can call. And in a neutron star, the universe has called it completely. Let me give you one more comparison, and this one is the most violent of all. Imagine standing 1 meter above the surface of a neutron star, holding a single small object in your hand, a pebble, a coin, anything light. Now let go. On Earth, the pebble would fall 1 meter and land with a soft tap. On a neutron star, the gravity is so ferocious that in the time it takes to fall, that 1 meter, the pebble accelerates to a speed approaching a sizable fraction of the speed of light. By the time it strikes the surface, it is moving so fast that the energy released in the impact is comparable to the detonation of a large fraction of all the nuclear weapons on Earth, all at once, from dropping a single pebble 1 meter. The fall itself, the simple act of letting go, becomes one of the most energetic events you could stage. Imagine it for a moment, because the strangeness lives in the details. You hold the small stone at arm's length above the iron-hard crust. You feel nothing yet in this impossible thought experiment, no warning, just a tiny weight resting in your fingers. You open your hand. There is no slow tumble, no gentle drop. The stone simply vanishes downward, snapping toward the surface faster than your eye could ever follow, crossing that single meter in a flicker. And where it meets the crust, there is a flash, a release of energy out of all proportion to the act. The the violence of a continent's worth of bombs born from the fall of a pebble. That is what gravity becomes when matter is this dense. Even the smallest gesture turns catastrophic. There is a way of feeling this number that I find more useful than any single comparison, and it has to do with what density really measures. Density is simply how much mass is crammed into a given amount of space, and the reason ordinary objects have the densities they do is almost entirely about empty space. A block of lead feels heavy because its atoms are relatively massive and relatively close together. But even in lead, even in the densest metals you can hold, the atoms are mostly hollow, with vast gulfs of nothing between each tiny nucleus and the electrons whirling far around it. Every solid thing you have ever encountered is, at the atomic level, almost entirely vacant, a sparse scattering of matter held apart by the stubbornness of electrons. The density of a neutron star is what you reach when you finally win the argument against that stubbornness, when gravity becomes strong enough to push the electrons aside and let the nuclei touch. When the nuclei touch, when there is no more empty space to remove, you arrive at a density that is roughly the same everywhere it occurs, because it is set by the size of atomic nuclei themselves. This is why neutron star matter always lands at this same staggering figure, a few 100 million tons in a sugar cube, regardless of which neutron star you measure. It is not an arbitrary number. It is the density of the atomic nucleus itself, scaled up to the size of a city. In a very real sense, a neutron star is a single colossal atomic nucleus, a piece of the inside of an atom blown up until it is 20 kilometers across and visible from across the galaxy. The thing you cannot see, the dense core hidden at the center of every atom in your body, has been taken and made enormous. And that is what you are looking at when you look at a neutron star. I find that this is the moment, more than any other, when people stop and look at their own hands. The matter inside an atomic nucleus is not exotic. It is in every atom of you, every atom of the air, every atom of the world. You carry an unimaginable number of these tiny dense cores inside you at this very moment. Each one a fleck of the same material that, gathered together and stripped of the emptiness around it, would become a neutron star. You are made of the stuff. It is only the arrangement, the generous emptiness that holds your atoms open, that keeps you from being impossibly heavy. Remove the emptiness, and what is left is the densest thing in the universe. Solidity, weight, the firm, ordinary world, all of it rests on a structure of mostly nothing, and a neutron star is what remains when the nothing is taken away. This density is also why we can be so confident neutron stars are real, even though no human will ever hold a piece of one. We measure their masses by watching them orbit other stars and tug on them with their gravity. We measure their sizes through the light and X-rays they emit. And when we put those numbers together, the mass of the sun or more, packed into a sphere the size of a city, the density that falls out is exactly this. Matter at the density of an atomic nucleus, a few 100 million tons in every sugar cube. The number is not a guess or a flourish. It is what the measurements demand. So the spoonful that outweighs a mountain is true. The pebble that falls like a bomb is true. And the deeper truth, underneath both of them, is the one that should make you look at your own hand a little differently tonight. The matter you are made of is almost entirely empty, held open by rules that gravity can break if it pushes hard enough. A neutron star is the proof, sitting in the sky, that everything solid is a temporary arrangement, and we have only described the surface. The truly bewildering part is what happens when you go inside, when you descend beneath that iron-hard crust and into the layers below, where matter takes forms that no laboratory on Earth could ever create. Part 5. Inside the Impossible. We have descended into the core of a neutron star before, on an earlier night when we asked what truly happens to matter when it breaks down inside one of these objects. Tonight, I do not want to retrace every step of that descent. But I do want to stand at the threshold again, just long enough to remind you of how genuinely alien the inside of a neutron star is, because everything we say afterward about gravity and magnetism and spin is happening on top of this hidden, churning strangeness. Begin at the surface. The outermost skin of a neutron star is a crust, and it is unlike any crust you have ever pictured. It is a solid lattice of atomic nuclei, locked into a rigid, crystalline structure, sitting in a sea of free-flowing electrons. This crust is thought to be the strongest material in the entire universe, billions of times stronger than steel. So strong that the forces required to crack it are almost beyond imagining. And yet, as we will see later, it does crack, and when it does, the consequences travel across thousands of light years. Press downward, beneath the crust, and the matter begins to change in ways that have no everyday counterpart. As the pressure climbs, the atomic nuclei become so overstuffed with neutrons that they can no longer hold them all, and neutrons begin to leak out, to drip free of the nuclei entirely. Physicists call this the neutron drip, and below it the matter becomes a strange mixture, a fluid of free neutrons flowing around the remaining nuclei. The deeper you go, the more the ordinary structure of matter dissolves, until the nuclei themselves are forced into shapes that sound almost playful for something so extreme. Under the crushing pressure, just beneath the crust, the nuclei are squeezed and stretched until they merge into long tubes and flat sheets. Physicists have given these shapes names borrowed from an Italian kitchen. There are rods of nuclear matter they call spaghetti, and flat layers they call lasagna, and a whole family of these forms goes by the collective name of nuclear pasta. It would be easy to laugh at the names, but the substance they describe may be the strongest material that exists anywhere, a layer of matter so resistant to being broken that nothing in the ordinary universe comes close. These whimsical names sit on top of something genuinely beyond our reach. Go deeper still, into the core itself, and the certainty runs out. We know the outer layers reasonably well, because we can model them with the physics we understand. But the very center of a neutron star sits at a pressure and density so extreme that no laboratory on Earth can reproduce it, not even for an instant, not even inside our most powerful particle accelerators. We are left to theorize, and the theories diverge into a handful of strange possibilities. The core may be an ocean of neutrons, packed even more tightly than above. Or the neutrons themselves may begin to dissolve, breaking apart into the smaller particles they are made of, the quarks, producing a kind of free quark soup that exists nowhere else. Or stranger particles called hyperons may appear, or the quarks may lock into an exotic state with a name and a behavior that has no parallel in the world we can touch. This is the genuine frontier, and I want to be honest with you about the limits of what we know, because that honesty is part of the wonder. We do not know what is at the center of a neutron star. We have a list of candidates and no way, at present, to walk up and check. The matter there is sealed inside an object we can never visit, under conditions we can never recreate, and the only way we have to read its secrets is indirect, watching how the star cools, how it spins, how it flexes when another star passes close. The deepest, densest matter in the universe sits inside a locked room, and we are trying to work out what is inside by listening at the door. There is one more clue worth mentioning, one that the stars themselves give us. Every so often, astronomers watching a spinning neutron star see it do something abrupt and unexpected. Its rotation, which is normally as steady as a clock, suddenly speeds up just slightly in an instant. These events are called glitches, and they are a window into the hidden interior. The leading explanation is that the inside of a neutron star is not entirely solid. Much of it behaves as a superfluid, a frictionless liquid that can flow without resistance. In this superfluid, the rotation is stored in tiny whirlpools, and when a great many of them suddenly let go at once and transfer their motion to the crust, the whole star jumps forward in its spin. We cannot see inside, but we can watch the star twitch, and from that twitch we deduce that there is a frictionless ocean hidden beneath the surface. Think about what it means that the strongest material in the universe and the deepest mystery in physics are stacked one on top of the other inside the same small object. The crust of a neutron star is so strong because the nuclei within it are locked together by forces and pressures that have no equal on Earth, forming a lattice that resists breaking with a stubbornness billions of times beyond steel. If you could somehow carve out a mountain of this crust material and set it on Earth, it would hold a weight that would shatter any ordinary substance instantly. And yet that crust, for all its strength, is only the thin outer skin of the object, perhaps a kilometre or two deep, on a star 20 kilometres across, a hard shell over an interior that grows stranger with every step inward. The reason the nuclear pasta matters, beyond the charm of its names, is that it represents matter being forced into configurations that simply do not occur anywhere else. In ordinary conditions, atomic nuclei are tiny, separate, round things, each keeping to itself. Under the pressure just beneath a neutron star's crust, they are pressed so close together that they begin to merge and reshape the way droplets of water on a window will merge into rivulets and sheets when there are enough of them packed closely enough. The competition between the forces pulling the nuclear matter together and the electric forces pushing it apart settles into these long tubes and flat plates, and the result is thought to be the strongest and stiffest material that can exist. The kitchen names are a way of making something genuinely alien feel approachable, but underneath the spaghetti and the lasagna is a substance that pushes the laws of nuclear physics to a place we can model only with our most careful theories. When you reach the core, the honest answer is that the theories begin to disagree with one another, and we have no way yet to decide between them. This is not a small gap in an otherwise complete picture. It is one of the genuine open frontiers of physics. The behavior of matter at these densities is described by something physicists call the equation of state, essentially the rulebook for how this matter responds to being squeezed, and we do not know that rulebook. Different rulebooks predict different things: a slightly different maximum mass before collapse into a black hole, a slightly different size for a star of a given mass, a slightly different signal when two of them collide. So when we measure those things, the sizes and the masses and the collision signals, we are not just cataloguing neutron stars. We are slowly, indirectly, reading the rulebook for the densest matter in existence, narrowing down which of the competing answers about the core could possibly be true. So this is the foundation that everything else rests on. Beneath the iron-hard crust lies a sea of dripping neutrons. Beneath that lie sheets and tubes of nuclear pasta. And beneath that, at the very center, lies a question, a form of matter we can name in 3 or 4 different ways, but cannot yet identify, the densest material in existence, hidden where we can never reach it. Keep that hidden core in mind as we climb back to the surface, because the gravity we are about to discuss, the gravity that bends light and folds bodies, is the same gravity holding all of that impossible matter in place. To understand how a neutron star can let you see the back of your own head, we have to talk about what its gravity actually does to space, to light, and to anything unfortunate enough to draw near. Part 6. Gravity that folds light. Gravity is the quiet force. On Earth, it is so gentle that we barely notice it, a soft and constant pull that keeps our feet on the ground and our coffee in the cup. We have to fall off something to be reminded that it is even there. But gravity is not weak. It only seems weak because we live on a planet whose mass, enormous as it is by human standards, is spread out across a sphere 13,000 kilometers wide. Concentrate that mass, shrink the distance, and gravity stops being gentle. On a neutron star, gravity becomes the most powerful force you could ever stand inside, and it does things to space itself that no human intuition is prepared for. Consider what your weight would become there. On the surface of a neutron star, the pull of gravity is something like 100 billion times stronger than the pull you feel right now. If you weigh what an average person weighs on Earth, then on a neutron star, you would weigh something on the order of 1 trillion times as much. There is no standing on such a surface, no walking, no resisting. The instant any ordinary object touched the crust, it would be flattened beyond recognition. Spread into a film no thicker than a single atom, its every structure crushed flat against the impossibly hard ground. You would not fall onto a neutron star. You would be smeared across it. Let me take you there for just a moment, into the impossible. Imagine you are standing, somehow, on the surface of a neutron star, protected by nothing but the suspension of physics that thought experiments allow. The ground beneath your feet is smoother than any polished metal, a crust flattened to within a fraction of a millimeter of perfect roundness by the merciless gravity. You try to lift a foot, and you cannot. Your body weighs as much as a mountain range now, pressed downward by a force that would fold you into the surface in an instant, if the rules let it. And then you look up, and you look out toward the horizon, and you see the thing that should not be possible. You see the back of your own head hanging in the sky in front of you. It happens because gravity does not only pull on matter, it pulls on light. Einstein understood this more than a century ago. A sufficiently strong gravitational field bends the very path that light travels, curving a beam the way a hill curves the path of a rolling ball. Near a neutron star, the bending is so severe that light leaving the surface does not travel in a straight line at all. It curves. A beam of light leaving the back of your head can follow the curve of space around the star and come back around to the front, entering your eyes from ahead. The image of the back of your head is carried around the star by the bending of light and delivered to your face. You see yourself from behind, because near an object this dense, straight lines are no longer straight. This same bending of light produces an effect that astronomers can actually observe from a safe distance, and it is one of our most powerful tools. When a neutron star, or any very dense object, passes in front of a more distant source of light, its gravity bends the light from that background source as it passes, distorting and sometimes brightening it. This is called gravitational lensing, and it lets us use the warping of space itself as a kind of natural telescope. By measuring exactly how the light is bent, we can test our theories of gravity in conditions far more extreme than anything available on Earth. The bending of light around a neutron star is not just a curiosity for a thought experiment. It is a confirmation that our understanding of gravity holds even at the edge of what gravity can do. And neutron stars give us more than lensing. Some of them orbit other stars in close pairs, and when they do, they become the finest testing grounds in existence for Einstein's general theory of relativity. As two such objects circle each other, their gravity is so strong and their motion so fast that the subtle predictions of relativity, effects far too small to detect in the gentle gravity of Earth, become large enough to measure with astonishing precision. There is a famous pair known as the double pulsar, a system where both stars are spinning neutron stars sending out regular pulses. Each pulse acts like the tick of a clock, and by timing those ticks, astronomers can track the orbit down to the finest detail. Every prediction Einstein made about how gravity should behave in such a system has come true, confirmed to a precision that is almost unsettling in its exactness. The strangest object in the sky turns out to be the most reliable witness we have to the deep nature of gravity. There is something humbling in that. The neutron star is so extreme that it should break our theories, and instead it confirms them. A century ago, a man sat with a pencil and worked out, from pure thought and a handful of principles, how gravity must bend light and warp time and drain energy from orbiting masses. And out in the dark, objects he never imagined in their full strangeness, objects that would not be discovered for decades after his death, obey his equations exactly. The gravity that would fold your body into a sheet 1 atom thick is the same gravity that, when we study it carefully, tells us that we actually understand something true about the universe. There is a subtler effect of this gravity that deserves a mention because it touches something we rarely think about: time itself. One of the deepest lessons of Einstein's work is that gravity does not only bend space, it also slows time. The stronger the gravitational field, the more slowly time passes within it, and near a neutron star, the field is so strong that the effect becomes large. A clock sitting on the surface of a neutron star would tick noticeably more slowly than a clock far away in empty space. If you could somehow hover near one of these objects and watch the distant universe, you would see the rest of the cosmos running fast, the stars wheeling, events unfolding more quickly than they should, because your own time had been dragged into a slower rhythm by the gravity beneath you. Time runs at different speeds in different places, and a neutron star is one of the places where that strange truth becomes impossible to ignore. This slowing of time is not a fantasy or a mere calculation. It leaves real marks on the light these objects emit. As light climbs away from the surface of a neutron star, struggling upward against that enormous gravity, it loses energy, and losing energy shifts its color toward the red end of the spectrum. By measuring exactly how much the light has been reddened on its way out, astronomers can read the strength of the gravity it escaped from, and from that work backward toward the mass and size of the star. The bending of light, the slowing of time, the reddening of escaping radiation, these are not separate curiosities. They are all the same underlying fact, gravity reshaping the behavior of light and time, written across these objects in ways we can actually observe and measure from the safety of Earth. And every one of these measurements has agreed with the theory, again and again, to a precision that should give anyone pause. There is something almost eerie about how well a set of equations written more than 100 years ago by a man working with chalk and thought continues to describe objects he could scarcely have imagined. Einstein never knew that neutron stars existed. The idea was only beginning to be taken seriously near the end of his life. And yet when these objects were finally found, decades later, spinning and flaring and bending light, exactly as we have described, they fell into line with his equations as though they had been waiting all along. The most extreme gravity we can study is also the most thorough confirmation we have that we understand what gravity is. So hold both of these things together as we move on. A neutron star's gravity is violent enough to crush a person out of existence and to bend light into a closed loop around itself. And it is precise enough, lawful enough, that we can use it to confirm the deepest theory of space and time we have. The terror and the order are the same force. But gravity is not the only field a neutron star wields. There is another force at work in these objects, one that does not crush but instead distorts, a magnetism so intense that it reshapes the empty vacuum of space and, on occasion, reaches across the galaxy to brush against the Earth itself. Part 7. Magnets that rewrite the vacuum. You have felt magnetism your whole life, though you rarely think about it. It is the force that holds a note to a refrigerator door, that swings a compass needle toward the north, that hums inside every motor and speaker around you. A refrigerator magnet carries a field strength of around 100 Gauss, Gauss being the unit we use to measure these things. The Earth itself, the entire planet, generates a magnetic field of only about half a Gauss at the surface, weak enough that a small magnet in your hand easily overpowers it. These are the magnetic forces of everyday life, modest and familiar. Now prepare to leave them very far behind. An ordinary neutron star carries a magnetic field of perhaps 1,000,000,000,000 Gauss, already a number with no earthly comparison. But a certain class of neutron stars takes this to a level that strains the language we have for it. These are the magnetars, the most strongly magnetized objects known to exist anywhere in the universe, and their fields can reach 1,000 trillion Gauss, a 1 followed by 15 zeros. To set that beside the refrigerator magnet is almost meaningless. It is like comparing the weight of a feather to the weight of a world. A magnetar's field is so far beyond anything in our experience that near one of these objects, the ordinary rules of physics begin to warp, and even truly empty space stops behaving the way it should. This is the part that genuinely unsettles physicists. We tend to think of the vacuum of empty space as simply nothing, a stage on which things happen but which has no properties of its own. A magnetar proves otherwise. In a magnetic field that strong, the vacuum itself becomes bifringent, meaning it bends light differently in different directions, behaving like a crystal even though there is nothing there. The emptiness gains structure. And atoms, if any were to stray near such a field, would be deformed beyond recognition. Their normally round electron clouds, stretched into long, thin needles, aligned with the field, pencil-shaped slivers of matter that could not exist anywhere else. Near a magnetar, nothing keeps its ordinary form. Not matter, not light, not even the vacuum. These fields do not just sit there quietly. They store an immense reservoir of energy, and sometimes that energy is released in a sudden and catastrophic event. Remember the crust, that lattice of nuclear matter said to be the strongest material in the universe. The magnetar's field threads through that crust and twists it, building up unbearable stress until the crust can take no more and fractures. The result is a starquake, a cracking of the surface that releases a burst of energy in the form of gamma rays, the most energetic kind of light there is. And these bursts are not minor. They are among the brightest flashes the universe produces. There is a famous example, and it shows just how far the reach of these objects extends. In late December of 2004, a magnetar known by its catalogue name, sitting roughly 50,000 light-years away from us, on the far side of our own galaxy, unleashed a giant flare. The energy released in a fraction of a second exceeded what our Sun produces in many thousands of years. And even though this object was tens of thousands of light-years distant, so far that its light had been travelling toward us since before human civilization began, the flare was powerful enough to physically disturb the upper atmosphere of the Earth. It compressed and rattled our ionosphere, the electrically charged layer high above our heads from across the entire width of the galaxy. A crack in the crust of a single dead star, 50,000 light-years away, reached out and touched our planet. Let that distance sink in, because it is the part that turns a fact into something closer to dread. 50,000 light-years is a span so enormous that light, the fastest thing there is, needs 50,000 years to cross it. And yet a single convulsion of one magnetar bridged that gap and left a measurable mark on the air above the Earth. If such an object were close to us, within a few tens of light-years, instead of tens of thousands, the consequences would be severe. Thankfully, no magnetar sits anywhere near that close. The nearest of them are safely thousands of light-years away, and the danger they pose to us is essentially nothing. But the fact that one can reach us at all, from the other side of the galaxy, is a reminder of the forces these objects command. To put their magnetism in terms closer to home, consider this. A magnetar's field is so powerful that, were one to drift to within a few hundred kilometers of the Earth, it would erase the magnetic strip on every credit card on the planet, wipe every hard drive, and pull the iron from the blood and the atoms from their arrangements long before that. It is, of course, a scenario that will never happen, a thought experiment to give the number a shape you can hold. But the shape it gives is a frightening one. These are objects that do not need to touch you to unmake the ordered matter of your world. Their influence is written into the fields around them, fields that bend light, deform atoms, and crack the strongest crust in existence. It is worth asking where such a monstrous magnetic field even comes from, because the answer connects back to the collapse we watched earlier. A star, before it dies, already has a magnetic field, usually a gentle one, threaded through its enormous body. When the core collapses, that magnetic field collapses with it, squeezed down, along with the matter, from something the size of the Earth to something the size of a city. And just as the spin accelerates when the core shrinks, the magnetic field intensifies when it is compressed. The field lines that were spread thinly across a vast surface are crushed together into a tiny one, concentrated by the same shrinkage that speeds up the rotation. For the most extreme magnetars, this simple compression may not be the whole story. Some process in the churning, newly born neutron star, a kind of dynamo driven by its violent early convection, may amplify the field further still. But the seed of it is that same collapse, the same catastrophic shrinking that creates everything else strange about these objects. The energy stored in a magnetar's field is almost beyond accounting. We are used to thinking of magnetism as a weak and tidy force, the gentle grip of a magnet on a paperclip. But a field of 1,000 trillion Gauss holds an energy density so high that the field itself becomes a reservoir of power, rivaling the star's own gravity and rotation. This is why magnetars are so violent. They have somewhere to draw that violence from. The starquakes and the giant flares are the field unloading a portion of its stored energy in sudden, catastrophic releases, the magnetic equivalent of an earthquake on a planet, except that the energy released in a single magnetar flare can exceed what the sun produces over thousands of years, all of it poured out in less than a second. There is nothing gentle left in a force pushed this far. And magnetars do not last forever in this state, which is part of what makes them precious to study. The extreme magnetic field that defines a magnetar also drains its energy relatively quickly, by cosmic standards, so a star spends only a fraction of its existence in this most violent phase, perhaps 10,000 years or so before the field decays and quiets. This means the magnetars we see are young, recently born from supernovae, caught in a brief and furious chapter of their lives. We are watching a fleeting stage, a flash of extremity that each of these objects passes through and then leaves behind. To catch a magnetar in the act of flaring is to witness one of the rarest and most powerful performances in the universe stages, and to know that the same object, given enough time, will eventually fall silent. And here is the thread that ties the magnetism back to everything else, because a magnetar does not only crack and flare, it also spins, and it is the spin, combined with the magnetism, that produces some of the most precise and beautiful signals in all of astronomy. A spinning magnet generates beams, and beams that sweep across the sky become a kind of cosmic lighthouse. To understand the lighthouse, we first have to understand the spin, and the spin of a neutron star is yet another of its quietly impossible features. These city-sized corpses of stars turn faster than almost anything you can picture, and the steadiness of their turning has given us some of the finest clocks the universe has ever offered. Part 8. The fastest clocks in the universe. To understand why a neutron star spins so fast, picture a figure skater. When a skater wants to spin faster, they pull their arms in close to their body, and without any extra effort, their rotation speeds up dramatically. This is one of the most reliable rules in physics, the conservation of angular momentum. When a spinning object shrinks, its spin must accelerate to compensate. The arms come in, the spin races up. It is not a trick, it is a law. Now apply that law to a dying star. The original star, before its collapse, was rotating slowly, turning perhaps once every few weeks, an enormous and leisurely wheel of gas. But then its core collapsed, shrinking from something the size of the Earth down to a sphere only 20 kilometers across. The skater did not just pull in their arms, the entire body shrank by a factor of tens of thousands. And so the spin accelerated by a staggering amount. A rotation that once took weeks now takes a fraction of a second. The newborn neutron star emerges from the collapse, spinning many times every second, a city-sized object heavier than the sun, whirling around faster than the blades of a kitchen blender. The numbers here are difficult to hold in the mind. A typical young neutron star might rotate several times each second. But the fastest ones, a special class called millisecond pulsars, spin hundreds of times every second. The current record holder turns 716 times per second. Try to picture that. In the time it takes you to say the word Mississippi, this object, more massive than our Sun, has completed over 700 full rotations. Its equator is moving at a sizable fraction of the speed of light, racing around the star tens of thousands of kilometers every second. And yet the star holds together, its monstrous gravity just barely winning against the tremendous force of that spin. What makes this spin so valuable to science is not just its speed, but its astonishing steadiness. A spinning neutron star is a flywheel of almost perfect regularity. With more than the mass of the Sun concentrated into such a small, dense, rigid ball, there is enormous resistance to any change in its rotation. It just keeps turning, tick after tick after tick, with a constancy that is hard to believe. In fact, the best millisecond pulsars keep time so steadily that, over long stretches, they rival, and in some respects, exceed the finest atomic clocks ever built by human hands. We make our most precise clocks in carefully shielded laboratories, and out in the chaos of space, the corpse of a star keeps better time than they do, simply by spinning. This precision is how these objects were first discovered, and the story of that discovery is one of the most human moments in the history of astronomy. In the year 1967, in Cambridge, England, a young researcher named Jocelyn Bell was studying the data from a new radio telescope, a sprawling field of wires and posts she had helped to build. The data came out as ink traced onto long rolls of paper, hundreds of meters of it, and she went through it by hand and by eye. And one night, she noticed something she would later describe as a bit of scruff, a small, odd smudge in the trace that did not look like the usual interference. Picture her there, leaning over the rolling chart, the pen scratching its line across the paper. The scruff returns, and when she examines it closely, she finds something that stops her. It is a signal, pulsing with perfect regularity, a sharp pulse arriving once every 1 1/3 seconds, as steady and precise as a ticking clock. Nothing in the known sky did that. Natural objects were not supposed to keep such exact time. The regularity was so uncanny, so machine-like, that for a short while the team could not rule out the strangest possibility of all, that they had stumbled onto a signal from another civilization. Half in seriousness and half in nervous humor, they labeled the source LGM, standing for Little Green Men. For a few days, a small group of scientists in England held in their hands a signal they could not explain, ticking out its rhythm from somewhere far out in space, and they did not know whether they had found a new kind of star or a message from the dark. They had not found little green men, of course. They had found the first pulsar, a spinning neutron star sweeping a beam of radio waves across the Earth with every rotation, and the perfect regularity that had seemed almost artificial turned out to be the natural metronome of a dead star's spin. But I love that they paused there, in the not knowing. It is one of the few moments in science where the data was so strange that careful, sober researchers genuinely had to consider that they might have heard from someone. The universe had produced something so precise, so clockwork, that it briefly impersonated intelligence. And the truth, when it arrived, was in its own way just as astonishing, a city of crushed matter, spinning hundreds of times a second, keeping better time than our finest instruments. There is a quiet injustice in the history of that discovery that deserves to be remembered. Jocelyn Bell was a graduate student at the time, and it was she who noticed the scruff, she who tracked it down night after night, she who confirmed that the signal was real and regular and not some flaw in the equipment. When the discovery was awarded the highest honor in physics some years later, the prize went to her supervisor and not to her. For decades, she carried that omission with a grace that itself became part of the story, and the world has since come to recognize her as the true discoverer of pulsars. I mention it because it is easy to talk about these objects as pure physics, as numbers and forces, and to forget that every one of these discoveries was made by a person, often a young person, leaning over data late at night, noticing something that did not fit. The universe does not hand us its secrets. Someone has to see the scruff and refuse to look away. The precision of these spinning clocks has turned out to be useful in ways that go far beyond simply finding them. Because a pulsar's ticks are so regular, any tiny disturbance in their timing tells us something. If a pulsar has a planet, the planet's gravity tugs the star slightly back and forth, and the ticks arrive a hair early and then a hair late in a repeating pattern, and from that pattern we can detect the planet. In fact, the very first planets ever found outside our solar system were discovered this way, not around an ordinary star, but around a pulsar, betrayed by the minuscule wobble they imposed on its otherwise perfect rhythm. The corpse of a star became the most sensitive scale in astronomy, weighing worlds by the trembling of its own pulse. And the usefulness reaches further still, out toward the practical dream of navigating the galaxy. Because we know the exact rhythm of many pulsars scattered across the sky, a spacecraft far from Earth could, in principle, listen to several of them at once and use the timing of their pulses to work out exactly where it is, the way a ship at sea once used the known positions of stars. It would be a galactic positioning system that needs no signal from home, built entirely from the ticking of dead stars. This is not merely a fantasy. Prototype versions of pulsar navigation have already been tested aboard the space station, using a dedicated instrument to track these cosmic clocks and demonstrate that a vehicle could indeed find its way by their light. The same precision that briefly looked like a message from little green men may one day guide our machines across the dark between the stars. That discovery opened a door, and through it came a whole population of these objects, each one revealing itself by the rhythm of its spin, because the spin is only half the story. A neutron star that spins and that carries a powerful magnetic field does something remarkable with that combination. It becomes a beacon. It sends beams of radiation sweeping out across space, and when one of those beams happens to cross the Earth, we see it blink. To understand how a dead star becomes a lighthouse, and how that lighthouse splits into the whole strange family of objects we have catalogued, we need to follow the beam itself, out from the magnetic poles and across the galaxy. Part 9. Lighthouses, binaries, and millisecond flashes. A pulsar is a neutron star caught in the act of being a lighthouse. The mechanism is elegant once you see it. The star spins, and it carries a powerful magnetic field, and from the two magnetic poles of that field, it sends out narrow beams of radiation, focused streams of radio waves or X-rays or gamma rays, pouring out into space. Here is the key detail. The magnetic poles of a neutron star are usually not lined up with the axis it spins around, just as the Earth's magnetic north is not quite at the geographic North Pole. So as the star rotates, the beams swing around with it, sweeping great circles across the sky, like the rotating lamp of a lighthouse on a coast. If one of those sweeping beams happens to point at the Earth as it passes, we detect a pulse. Then the beam swings away, and we detect nothing. Then the star completes another rotation, the beam sweeps past us again, and we detect another pulse. From our vantage point, the steady spin of the star becomes a steady blinking, a regular flash arriving with every rotation, which is exactly the rhythm that Jocelyn Bell first saw traced on her rolls of paper. The pulsar is not actually pulsing, it is shining steadily and turning, and we sit in the path of its beam, catching a flash each time it comes around. Because the spin is so regular, the flashes are too, which is why these objects make such extraordinary clocks. Not all neutron stars announce themselves this way, though, and the family of these objects is larger and stranger than the pulsars alone. We have already met the magnetars, the ones with the most extreme magnetic fields, the ones that crack and flare. Some of these overlap with pulsars. Some reveal themselves mainly through their violent bursts rather than steady beams. But there is another whole category that comes to life only because a neutron star does not always live alone. Many stars are born in pairs, two stars orbiting each other, and when one of them dies and becomes a neutron star, the dead star and its living companion remain locked together in their orbital dance. And that pairing produces some of the most dramatic behavior of all. When a neutron star orbits close to an ordinary companion star, its ferocious gravity begins to pull material off the surface of the companion. The stolen gas does not fall straight in. Because both stars are orbiting, the material spirals inward, forming a flattened, swirling disk around the neutron star, a structure we call an accretion disk. As the gas spirals down through this disk, it is compressed and heated to staggering temperatures, millions of degrees, hot enough to glow fiercely in X-rays. These systems are called X-ray binaries, and they shine brightly in a part of the spectrum our eyes cannot see, lit by the heat of matter being devoured. Sometimes the feeding turns explosive. As stolen gas piles up on the surface of the neutron star, the pressure and temperature at the bottom of that accumulating layer climb higher and higher until the material ignites all at once in a runaway thermonuclear flash. A burst of energy erupts from the surface, brightening the system enormously for a brief time before it settles and the slow accumulation begins again. These thermonuclear bursts are, in a sense, a smaller cousin of the processes that power the stars themselves, except here they happen as sudden flares on the skin of a dead star, fed by matter, torn from a living one. A neutron star, in a binary, is a kind of cosmic parasite, drawing the life from its companion and burning it in flashes. There is one more phenomenon worth bringing into this part, because it is one of the genuine mysteries of modern astronomy, and neutron stars sit near the center of it. Across the sky, telescopes occasionally catch fast radio bursts, brief and brilliant flashes of radio energy that last only a few thousandths of a second and then are gone. In that tiny instant, one of these bursts can release as much energy as the sun pours out in days. For more than a decade, their origin was a complete puzzle. They came from far across the universe, from distant galaxies, and no one knew what could produce a flash so powerful and so short. To appreciate how strange these flashes are, consider the energy and the speed involved together. A fast radio burst lasts only a few thousandths of a second, far shorter than a single blink, and yet in that flicker it can release as much energy as our sun pours out over the course of days. For something to produce that much energy in so brief an instant, it must be small and it must be extreme, because the shortness of the flash itself sets a limit on how large the source can be. A burst lasting a millisecond cannot come from an object much larger than the distance light travels in a millisecond, which is only a few hundred kilometers across. So whatever is making these bursts is compact, far smaller than an ordinary star, and capable of releasing staggering energy in a heartbeat. That description fits a neutron star almost perfectly, and it fits a magnetar, with its vast reservoir of magnetic energy, better than anything else we know. The answer, at least for some of them, now points back to neutron stars, and specifically to magnetars. In the year 2020, a magnetar within our own galaxy produced a fast radio burst, the first ever traced to a known source, and it confirmed what many had suspected. The extreme magnetic environment of a magnetar, with its starquakes and its sudden magnetic upheavals, can apparently generate these millisecond flashes of radio energy. Not every fast radio burst has been explained, and whether magnetars account for all of them, or only some, remains an open question. But the connection is real, and it means that these fleeting flashes from the far reaches of the universe may be the voices of the same objects we have been describing all along, the crushed and spinning corpses of dead stars calling out across billions of light years. The accretion that lights up an X-ray binary also does something fascinating to the neutron star itself, something that closes a loop in our story. When a neutron star pulls a steady stream of matter off a companion, that infalling material does not just heat up and glow. It also carries momentum, and as it spirals down onto the surface, it spins the neutron star up, faster and faster, the way water pouring onto a paddle wheel turns it. Over millions of years of feeding, a neutron star that had slowed down with age can be wound back up to tremendous speeds, hundreds of rotations per second, reborn as one of those millisecond pulsars that keep better time than atomic clocks. The fastest spinning stars in the universe, in other words, are often old stars that have been fed back to life by a companion, recycled, spun up by the very matter they stole. The record holder, turning 716 times a second, almost certainly earned that speed this way by a long meal at the expense of a neighbor. This connects the lonely beacon of a young pulsar to the parasitic feeding of a binary and shows that these are not entirely separate kinds of object, but often the same object at different stages of a long and strange life. A neutron star can be born spinning fast and bright, slow down over millions of years as it radiates its energy away, fade towards silence, and then, if it happens to have a companion close enough to feed on, be spun back up into a blazing millisecond pulsar for a second act. The catalogue of types we have built, the pulsars and magnetars and X-ray binaries, is in part a catalogue of chapters in these objects' lives, snapshots of dead stars at different moments in stories that stretch across the entire age of the galaxy. That these bursts can be used as tools makes them even more interesting. As a fast radio burst travels across the universe to reach us, it passes through the thin gas that fills the space between galaxies, and that gas subtly smears the signal, delaying some of its frequencies more than others. By measuring that smearing, astronomers can weigh the matter the burst passed through on its journey, using these flashes from dying stars to map the otherwise invisible material strewn across the cosmos. The strangest objects keep turning out to be useful, again and again. And the strangest event of all, the one that brings two of these objects together, is where we turn next. Because when two neutron stars find each other, the result is a collision that shakes the very fabric of space and forges the most precious metals in existence. Part 10. When two of them collide. Imagine two neutron stars bound together in orbit, two city-sized objects, each heavier than the Sun, circling each other in the dark. They have been doing this for a very long time, perhaps for hundreds of millions of years, two dead stars locked in a slow gravitational embrace. But the orbit is not stable forever. As they swing around each other, they stir the fabric of space itself, sending out ripples called gravitational waves, and those ripples carry energy away from the system. Bit by bit, orbit by orbit, the two stars lose energy and draw closer together. And as they draw closer, they move faster, and as they move faster, they radiate even more strongly, and the whole process accelerates toward an ending that is both beautiful and violent. In the final moments, the two neutron stars are whirling around each other hundreds of times every second, their surfaces nearly touching, the space around them ringing with gravitational waves like a struck bell. They spiral inward faster and faster, and then they meet. Two of the densest objects in the universe slammed together at a sizable fraction of the speed of light. The collision is less energetic than the supernova that created each of them, but it is still one of the most powerful events the cosmos produces. A detonation that briefly creates conditions not seen since the early universe and flings a spray of neutron-rich matter out into space. For most of human history, an event like this would have been completely invisible to us. It happens too far away to see with any ordinary telescope, and the most important signal it produces is not light at all, but the trembling of space itself. To detect that trembling, humanity had to build something almost as improbable as the neutron stars we were trying to hear, an instrument sensitive enough to feel a ripple in space far smaller than the width of a single atomic nucleus. We built it, and in the year 2015, it heard its first signal, the merger of two black holes, opening a brand new way of listening to the universe. And then, 2 years later, it heard something even more remarkable. Let me take you to that morning, because it is one of the great moments in the history of science. It is the 17th of August, 2017. In two enormous detectors, one in one corner of the United States and one in another, laser beams run down tunnels kilometers long, watching for the faintest shiver in the length of space. And on this morning, the shiver comes. The detectors trace a signal that rises in pitch over about 100 seconds. A long, rising chirp, the unmistakable song of two heavy objects spiraling together. But this signal is different from the black hole mergers heard before. It is lighter, longer, and it carries the signature of two neutron stars somewhere around 130 million light-years away in a distant galaxy. And then, just 1 7/10 seconds after the gravitational waves cut off, a satellite watching the sky in gamma rays catches a short, sharp burst of high-energy light from the same patch of sky. The two signals, the tremble of space and the flash of light, have arrived almost together after traveling for 130 million years across the universe. Word races between observatories around the world. Telescope after telescope swings toward that region of sky, hunting through the candidate galaxies, and within hours they find it, a new point of light glowing in a galaxy where nothing had been before, the fading fireball of the collision, an event astronomers had predicted but never seen. They call it a kilonova. Stop and consider what those detectors actually accomplished, because it is one of the most improbable feats of engineering humans have ever managed. A gravitational wave is a ripple in the fabric of space itself, and by the time one reaches us from 130 million light-years away, it is almost unimaginably faint. As it passes through the Earth, it stretches and squeezes everything it touches, but only by the tiniest amount, a fraction of the width of a single proton over a distance of several kilometers. To detect that, we built instruments with laser beams running down tunnels 4 kilometers long, precise enough to notice when those tunnels change length by less than the width of an atomic nucleus. We made a ruler sensitive enough to measure a change thousands of times smaller than the particles that make up the ruler itself. And it worked. On that August morning, that almost absurd sensitivity caught the faint shiver of two dead stars touching 130 million years after it happened. There is a humbling kind of timing in it too. The light and the gravitational waves from that collision left their galaxy 130 million years ago, when the dinosaurs still walked the Earth, and they traveled through the dark all that time, side by side, neither overtaking the other. The gravitational waves and the gamma rays arrived within about 1.5 seconds of each other after a journey of 130 million years, an agreement so close that it confirmed gravity and light travel at the same speed to an extraordinary precision. Settling a question physicists had wondered about for a long time, we did not arrange this. We simply built the instruments, pointed them at the sky, and waited, and the universe delivered an answer that had been on its way since before our species existed. In that single event, humanity did something it had never done before. We observed the same cosmic catastrophe in two completely different ways at once, through the ripples of gravity and through the light of the explosion, confirming that they came from the same source. It was the true beginning of what we call multi-messenger astronomy, the practice of studying the universe not through light alone, but through several different kinds of signal together, each telling part of a story that none could tell on its own. For the first time, we had heard two dead stars collide and seen the light of their collision, and the two accounts agreed. The collision gave us something else too, a new way to measure the universe itself. When two neutron stars merge, the gravitational waves carry a clean record of how powerful the event truly was, which tells us how far away it must have been to appear as faint as it did. And because we also saw the light of the kilonova, we could identify the exact galaxy it came from and measure how fast that galaxy is moving away from us as the universe expands. Put those two numbers together, the true distance from the gravitational waves and the speed from the light, and you have a fresh, independent way to measure the expansion rate of the entire universe, a quantity that has been the subject of one of the deepest disagreements in modern cosmology. Astronomers gave this kind of event a name, a standard siren, a single collision that doubles as a cosmic measuring stick. From two dead stars touching, 130 million light-years away, we drew a new ruler for the size and age of everything. This is what astronomers had hoped multi-messenger astronomy might offer, and the first true neutron-star merger delivered it on the very first try. A single event confirmed where the heavy elements come from, proved that gravity and light travel at the same speed, tested our theories of dense matter, and handed us a new way to weigh the expansion of the cosmos. No other observation in recent memory has answered so many separate questions at once, and it happened because for the first time we were not limited to a single kind of signal. We listened with our gravitational wave detectors, and we looked with our telescopes, and the universe told us a story that neither sense alone could have understood. But the most extraordinary part of that night was not the gravitational waves, remarkable as they were, and not the gamma-ray flash. It was what the fading glow revealed in the days that followed. As astronomers watched the light of the kilonova evolve, measuring its colors as it dimmed, they saw the unmistakable fingerprint of newly created heavy elements, vast quantities of them, freshly forged in the collision and flung out into space. The merger of two neutron stars had just manufactured a fortune in precious metals before our instruments, and in doing so, it answered a question that had haunted science for generations. Where do the heaviest elements in the universe actually come from? The answer was glowing in the data, 130 million light-years away. And that answer leads us to the most intimate part of this entire story, because the metals made in collisions like that one did not all stay out there in the dark. Some of them ended up here, on Earth, in our world, and in our hands. Part 11. The Gold in Your Hands. For most of the history of science, we understood where the common elements came from. The hydrogen in water was forged in the first minutes after the birth of the universe. The carbon in your body, the oxygen you breathe, the iron in your blood, all of these were cooked inside ordinary stars and scattered when those stars died. This was one of the great triumphs of 20th century astronomy, the realization that we are, quite literally, made of star material. But there was always a stubborn gap in the story, and the gap was at the heavy end of the periodic table. The elements heavier than iron, the gold and the platinum, the silver and the uranium, could not be made by the ordinary fusion that powers a star. They required something more extreme. The reason has to do with that same wall we met earlier, the wall of iron. Fusing elements together releases energy only up to iron. Past that point, building heavier elements consumes energy rather than producing it, so the cores of ordinary stars simply cannot make them. To forge gold, you need a place flooded with free neutrons, so densely packed and so fast-moving that atomic nuclei can swallow neutron after neutron in quick succession, building themselves up into heavier and heavier elements before they have a chance to break apart. Scientists call this the rapid neutron capture process, and for a long time we were not entirely sure where in the universe conditions that extreme actually existed. A merging pair of neutron stars is exactly such a place. When two neutron stars collide, they tear off and fling out a spray of their own matter, and that matter is made of almost nothing but neutrons, the densest neutron-rich material in existence. In the chaos of the collision, that spray becomes the perfect forge. Atomic nuclei in the debris capture neutrons in a frenzy, racing up the periodic table, building gold and platinum and the whole family of heavy elements in a matter of seconds. The kilonova that astronomers watched fade in 2017 was glowing precisely because of this, lit by the radioactive heat of newly minted heavy elements. A single such collision is estimated to produce many times the mass of the Earth in gold and platinum group metals alone, scattered outward into space to drift among the stars. Now follow that gold forward in time, because this is where the story comes home. The metals flung out by neutron star collisions long ago did not simply vanish into the dark. They mixed into the clouds of gas and dust that drift between the stars, the same kind of clouds we talked about at the very beginning, the nurseries where new stars and planets are born. And when our own solar system formed, some 4.5 billion years ago, it formed from a cloud that had been enriched by the deaths and collisions of earlier stars, a cloud already seeded with gold and platinum forged in ancient catastrophes. That gold settled into the young Earth. It is in the planet beneath you, and some of it, eventually, was dug up and shaped and worn. So consider, for a moment, the gold in a wedding ring. Consider the thin layer of gold inside the electronics you use every day, the platinum in a catalytic converter, the precious metals woven through the technology of modern life. Every atom of that gold was made in the collision of two dead stars, two neutron stars that spiraled together and shattered, perhaps billions of years before the Earth even existed. The most violent, most extreme objects in the universe are also its jewelers. The same crushed and terrifying matter we have spent this whole night describing is the origin of the most treasured metals humans have ever held. When you look at something gold, you are looking at the debris of a collision so powerful it bent the shape of space. There is something that turns over in the chest when this finally lands, a shift from terror to a kind of tenderness. We began this journey with a spoonful of matter that outweighs a mountain, an object so extreme it seemed almost hostile, a catalogue of crushing gravity and atom-bending magnetism and surfaces that would erase a human being in an instant. And it is all true. These objects are as extreme as anything in existence. But that same extremity, that same violence, is woven into the most intimate objects of human life. The ring on a hand, the wire in a phone, the matter we exchange as a symbol of love, was made in the death collision of stars. The terror and the treasure are the same material. The monster and the jeweler are the same object. This is the part of the story I find hardest to let go of and the easiest to fall asleep thinking about. The universe does not separate the beautiful from the terrible. It made the gold in the same furnace that made the nightmare. The neutron star is a thing that would crush you out of existence, and it is also the reason there is gold in the world to be crushed into a ring. Both things are true at once, and neither cancels the other. We are surrounded, quietly, by the work of these objects, wearing it, using it, exchanging it, almost never knowing where it came from. For a long time, scientists thought that another kind of event, the supernova explosions of ordinary massive stars, might be the main source of these heavy elements. And supernovae do make some of them. But the merger of two neutron stars appears to be a far richer forge, and the reason comes back to what these objects are made of. An ordinary supernova has to manufacture its neutrons in the moment of explosion, and there are only so many to go around. A neutron star, on the other hand, is already almost nothing but neutrons, a city-sized ball of the exact ingredient the heavy element process is starving for. When two of them collide and fling out their debris, that debris is the most neutron-rich material the universe has to offer, and the heavy elements build themselves with a speed and abundance that an ordinary supernova cannot match. The kilonova astronomers watched in 2017 confirmed this directly. The sheer quantity of gold and other heavy metals in that single event was more than enough to account for these elements being as common as they are. It is worth letting the quantities land because they are staggering in their own right. A single neutron star collision is estimated to forge many times the entire mass of the Earth in gold and platinum group metals alone in a few seconds and hurl it outward into space. Every collision is a treasury beyond any human reckoning of wealth, more precious metal than has ever been mined or ever could be, created in an instant and scattered to the winds of the galaxy. And it has happened countless times across the long history of the universe, each event seeding the gas between the stars with a little more of these heavy elements, slowly enriching the cosmos collision by collision, so that by the time our solar system formed, there was gold in the cloud to become part of the Earth. When you hold something gold up to the light, then you are holding the end of an unimaginably long chain of events. Two massive stars had to be born, live their short and furious lives, and die in supernovae, each leaving behind a neutron star. Those two neutron stars had to find themselves bound in orbit, and then spend hundreds of millions of years slowly spiraling together, shedding energy into ripples in space, before finally colliding and forging the gold. That gold had to drift through space, mix into a cloud, and happen to be present when our sun and its planets condensed out of that cloud. It had to settle into the Earth, survive the planet's violent formation, and rise close enough to the surface to be found. And then a human being had to dig it up and shape it and place it on a hand. Every step of that chain runs through the death and collision of stars, and almost no one wearing gold has any idea. And yet, for all of that, the deepest question about neutron stars remains unanswered. We have followed them from birth to collision, watched them spin and flare and forge the elements, and confirmed Einstein's gravity against their pull. But the thing at the very center of them, the matter in their cores, still hides from us. The most precious metals in the universe came from these objects, and we still cannot say for certain what their hearts are made of. To close out our night, I want to return to that locked room at the center, and to the strange comfort of admitting that there are things, even now, that we simply do not know. Part 12. The locked room at the center. We have come a long way tonight, from a cloud of cold gas to the collision of two dead stars, and through all of it, there has been one question we kept setting aside, promising to return to it. That question is the simplest one of all, and it is the one we cannot answer. What is matter when you push it this far? What, exactly, is at the center of a neutron star? We know so much about these objects. We know how they are born, in the collapse of a giant star and the fury of a supernova. We know their size and their mass with real precision, a city's width holding more than the sun. We can measure their spin to a staggering accuracy, time their pulses against our finest clocks, watch their light bend, feel the ripples they send through space when they collide. We have read the fingerprints of the gold they forge. By almost any measure, neutron stars are among the best-studied exotic objects in all of astronomy. And yet, at the very center, where the pressure climbs beyond anything that has ever existed inside a human machine, our knowledge simply runs out. The trouble is that we cannot build the experiment. To know for certain what matter does at the core of a neutron star, we would need to recreate those conditions, densities beyond the nucleus of an atom, pressures with no equal anywhere, and hold them steady long enough to look. No laboratory on Earth can do this. Not our greatest particle accelerators, not for the briefest instant. The core of a neutron star is sealed inside an object we can never visit, under conditions we can never reproduce. It is, in the most literal sense, a locked room, and the answer to one of the deepest questions in physics is sitting inside it, just out of reach. So we are left to guess, carefully and cleverly, from the outside. Perhaps the core is simply neutrons, packed more tightly than anywhere else. Perhaps, under that final crushing pressure, the neutrons themselves break apart into the smaller particles they are made of, the quarks, forming a free-flowing quark matter that exists nowhere else in the universe. Perhaps stranger particles appear, or the quarks lock into an exotic ordered state with no name in everyday speech. Each of these possibilities is a different answer to the question of how heavy a neutron star can become before it collapses the rest of the way into a black hole, and we do not yet know which is true. The matter at the center is one step short of vanishing, frozen at the very edge of what the universe permits, and we are reading its nature off the way it cools and spins and trembles, like working out the contents of a sealed box by its weight and the sound it makes when it is moved. But the tools are getting sharper, and this is where the wonder turns toward the future. There is an instrument on the space station right now whose entire purpose is to measure the size of neutron stars more precisely than ever before, watching the X-rays from their hotspots to pin down exactly how big they are, because their size is a direct clue to what their interiors are made of. Every time two neutron stars collide, and we catch the gravitational waves, the exact shape of that signal carries information about how their matter behaved as they were torn apart. Another reading from the locked room. As our detectors grow more sensitive, as we catch more mergers and time more pulsars and measure more sizes, the list of possible answers slowly narrows. We may not have the answer yet, but we are closing in on it, one faint signal at a time. There is a particular puzzle within this mystery that shows just how much hangs on the answer, and it is worth understanding before we let the night close. We have found neutron stars that are surprisingly heavy, around 2 1/5 or even 2 1/3 times the mass of the Sun, and each time we find a heavier one, it rules out some of the possible rulebooks for the core. The reason is simple to state. If the matter in the core is soft, easily squeezed, then it cannot hold up much weight before collapsing into a black hole, so very heavy neutron stars should not be able to exist. The fact that they do exist tells us the matter at the center is stiffer than some theories allowed, pushing back harder against gravity. So every heavy neutron star we discover is a vote, narrowing the field of possible answers about what that hidden matter really is. We are, in a real sense, letting the universe run the experiment we cannot run ourselves, and reading the results off the masses of the objects it produces. There is also a strange grey zone right at the boundary between the heaviest neutron stars and the lightest black holes, and it is one of the most tantalizing open questions in the field. Somewhere around 2.5 to 5 times the mass of the Sun lies a range where we are genuinely unsure what we are looking at. Is a compact object in that range the heaviest possible neutron star, matter held just barely short of collapse? Or is it the lightest possible black hole, matter that lost the fight and disappeared behind a horizon? We have detected objects sitting right in this uncertain band and could not say for certain which they were. The line between the densest visible matter and the disappearance of matter altogether is not a sharp one in our knowledge. It is a blurred and contested frontier, and exactly where it falls depends on the same rulebook we cannot yet read. I want to leave you with the strangeness, rather than a tidy resolution, because the strangeness is the truer thing. The densest matter in the universe is made of the same ingredients as you are. The protons and neutrons in a neutron star are the same protons and neutrons in your own body, in the chair beneath you, in the walls of the room. The only difference is how hard they have been pushed. Push ordinary matter far enough, squeeze the emptiness out of it, and it becomes something that bends light around itself and outweighs a mountain in a spoonful. There is no exotic new substance required. There is only the same matter we are all made of, taken one step too far. That is the thought I find myself turning over as the night gets late. The neutron star is not a thing apart from us. It is what our own matter becomes at the limit, the same particles under unimaginable pressure, the everyday made monstrous. We started by saying you could stand on one of these objects and, because of the bending of light, see the back of your own head. And in a quieter sense, that is what the whole study of neutron stars has turned out to be. We look out at the most extreme objects in the universe, and we end up looking back at ourselves, at the matter we are made of, pushed to the very edge of what is possible. The terror and the wonder were always the same thing. They always are. So, as you drift off tonight, let the questions stay open, the way the best questions do. Somewhere out there, in the dark between the stars, hundreds of millions of these objects are turning, keeping perfect time, holding a secret at their centers that we have not yet learned to read. There is no rush to solve it. The neutron stars will keep spinning, patient as gravity, for longer than we can imagine, and we will keep listening, a little closer to the answer every year. And the gold will keep catching the light, quietly carrying its origin in the death of stars, on the hands of people who will never know. Rest easy. The universe is stranger than we feared, and more generous than we knew, and it will still be there, turning when you wake.